My name is Long. I'm a researcher at the Institute for Computational Design of Stuttgart. Today I want to present to you the little project that I've been working over the past 2 days called Dynashape. It's a geometric form filing and optimization tool that runs within Dynamo. So the overall idea is that as usually designers, when they design complex form, they have a certain kind of constraints. For example, here we have a surface that is made up of quads. Each quad is planar. In fact, not only they're planar, but their vertices lie also on like a circle because it has some like fabrication advantage, for example. And the form is actually something emerged out of the constraint. So as opposed to like having a curved surface, which you then subdivide and try to rationalize it to something that you can manufacture. This is like a more bottom-up process where you have a little constraint that works together and give you the form as an emerging result. So I want to have this kind of tool that runs inside Dynamo interactively. So this is something that I have conceived a long time ago. But finally, I actually have the time to come here and actually start do some proper coding. So the underlying mathematical framework was actually developed at EPFL in Switzerland, and they published this framework in the paper called Shape Up. And this idea of geometric form filing has been popularized and like democratized in the computational design community, especially by the kangaroo physics tool for Grasshopper. And I want to bring this kind of capabilities and power to Dynamo. So over the past 2 days, I developed this custom plugins for Dynamo called Dynashape. Basically, it consists of a geometric solver that takes in a set of constraints, and these constraints act on the particles or the nodes. Okay, so at the moment I already kind of implemented some of the basics constraints that I call goals. So for example, you have the goals that ensure that the two lines will always have equal length, or they have to be parallel, or like they have to always align in certain directions. So all of the goals act on particles, and the lines basically just follow the goals. So the lines just like follow the particles. So let me see if I can switch to Dynamo. All right, so I've been told that I should speak closer to the microphone while also control the mouse. So let's see if I can do that. So here's a scenario where this is a pretty simple goal. It takes in a set of points and try to bring these points on circles of arbitrary orientations and radius. So this goal is pretty simple, and when I run it through the solver, it like immediately. Hang on a second. Let me see if I can. Okay. All right. So at first you have these points actually in 3D. They're not on a circle, and then when I run this over, you see that they will immediately snap to a circle. Okay. So let me see. So it's 3D for now, and then I snap. I run this over. Okay. So they cover the circle, and I can verify that they actually lies on a circle, like this art here. So this goal is very simple, and you get a result right away, and probably you don't even need a solver to like solve this simple geometric problem. However, when you have multiple goals that act on the same set of particles, and these goals are usually conflicting, then these goals actually start to like become like a useful design tool. So let me again. Right here we have a more complicated setup with a bunch of particles with initial random position. Now we want to apply some constraint on these particles such that only particles in the same row or columns have to be on circles, and they have to have equal length within that row or column. So each particle is subjected to more than one goals that are usually conflicting. Also, the four corners must also be anchored at some user defined position. So those are extra constraints. And if I run the solver, okay, so they actually snap into this position. And so now let me rotate the view a little bit, and you will see that they lies on the circle and they try to be as equal length as possible. So the surface is kind of emerging from this constraint. Now the designer can come in and move these anchors around, and the solver will keep updating and try to satisfy all these goals as much as possible. So all the goals can either be fully satisfied, or if the system is over-constrained, then the solver will try to find the best compromise that minimizes the error to all of the goals. Right, so if I move one of the anchors here, for example, I move this one up a little bit, so the solver will update. See, so the solver will update immediately and try to maintain all of those constraints. Okay, so let me show you another complicated example. So I have here a little system that makes up voxels. So the constraint here is that voxels want to be a cube of unit length. However, they will be subjected to other constraints. Like for example, the corner must go up to the anchor there. And clearly in this situation, there's no way that all the constraint will be satisfied. So the solver will try to come up with a solution that provide the best compromise for all of these conflicting constraints. Okay, so let me get on it. So that is the best compromise position. So as you can see, it's a bit laggy here, but it turned out that if you look at the time for the solver, each iteration actually takes only 30 milliseconds to run. It's actually only about 10 milliseconds for 10 iterations per display. So the reason why it's so laggy because Dynamo display is kind of slow. So each time we have to generate this bunch of lines, so it's slow down. So, but if I turn off the light display, then it will be fast enough and I can start to interact with that. Okay, I'm going to switch off the lights now, and it's way much faster. Okay, and I can come in and interact with that. So if I move the I move one of the anchor points around, then the shape will change immediately. Okay, so each of them will still try to be a cube as much as possible within and still respect those four movable anchor points. Okay. All right. So that is what I got so far. So my intention is that I make this tool open in both sense that it's open source, and it's open in the sense that the constraints are open for the designer to define. So I will expose some sort of simple API, and the designer can come in and use C# or R and Python to define their custom constraints, and they can plug the constraint to the same solver node, and it will work together with the other constraints. Okay. So let me switch back. And one reason why I'm so excited to have this running in Dynamo is because now we can combine this with the all of the other tools in Dynamo, for example, the parametric exploration tools such as Project Fractal. So instead of imagine moving all of the anchor points manually or set the stiffness or the strength of the code manually, you can like treat them as generic parameters and you can run them through this parametric exploration tool. So for each solution, for each set of parameters, the solver gonna update until you reach like some final static shape. And as you see, it takes quite a few of iteration to update. So that's why this thing is suitable to run on a cloud base where you have like a bunch of computer nodes that run the same dynamo graph in parallel. Okay, and then you can like generate a bunch of constraint-based forms, right? So that's something that I hope to do next. In addition to keep adding more into the constraint libraries, right? Right. So essentially that's So this is the first time I attend a hackathon actually, let alone an AEC hackathon. So it has been great fun. I hope to we keep doing this next year in Germany because I don't think I will have any chance to go to the US soon. Consider this political climate. All right. All right. Thank you.
That's very impressive. Maybe you want to stick around just for questions if they're want to, because we need to. Any questions for sure?
So it was just want to know where you are going to exactly to use this. What is the need, or what does it solve in this case? If you can clarify this.
About this slide or about the tool in general?
This the problem, business problem here.
The problem is that you have a constraint, you want to find a shape that satisfies those constraints as much as possible. And it's difficult. I mean, if you have a simple constraint, then like the designer can even sketch out a piece of paper. Yeah. But if you have like more than one constraint, like you have a lot of curved surface and you want to have like panels that is sensible, then this kind of tool will allow you to achieve those shapes.
So it means that you find those basic cubes, or for example, that it calculates all of them, that certain object or solid.
You can embed the rules and then still have the designer play, but instead of post-rationalizing some curvy thing into something that could be built, the designer feels like they have a lot of control, but it's always within the domain of what could be built.
So whenever the designer moves, say one of the anchor points, then the shape will update to satisfy the user control, but still keep all of these lines on the circle because probably that has some advantage, for example. Yeah.
Okay, thank you.
So how does this differ from the PQ mesh sort of ideas that have been floated around, like the Evolute tools and other guys that have done trying to maintain planarity and quad meshes?
Because this is more than just planarization goal. It's like you can have goal to keep lines in parallel. You can have goal that maintain angles. For manufacturing, for example, you don't want like the panels or the quads to be like form into a small angle, for example. So it's up to the designer and also me to like define this custom constraint library. And it's worked iteratively. I think Evolute is more, I'm not sure if it's iterative or it's more like an analytical solution where it snaps to the solution right away.
My question is, are the constraints more design-oriented or structure-oriented? So if I move like a point, the constraints that I enter, are they assured that the building was, the construction was safe?
As long as you can capture the structural condition as geometric constraint, for example, you can maintain the length between two particles, and if you can translate it to an actual displacement vector that acts on the vertices, then it will be able to work with other constraints. Yeah.